All right, let's get right into it. Today, we're stepping away from the textbooks and onto the plant floor. We're going to talk about something you just can't learn in a classroom: how real engineering skill is forged by facing down the kind of messy, high stakes problems that don't have a simple answer in the back of the book. This right here, this is the core idea. Theory is absolutely your foundation. You need it. But it's out there in the trenches, solving a real problem with real consequences, that you truly become an engineer. We've got two incredible stories for you that show this perfectly. One is a tricky little pump trip that seems simple, and the other, well, the other was a massive failure that caused a full-blown plant shutdown. So let's open up our first case file. It's a bit of a mystery, really. The scene is a power plant, and we're looking at a critical lubrication pump for a gearbox. The setup is simple. If the oil pressure gets too low, the pump trips. It's a basic but absolutely crucial safety system. Okay, so the pump trips out of nowhere. The team goes to investigate, and they find a blown fuse. Easy fix, right? They swap it out, the pump fires right back up, everything looks good. But then, about an hour later, same alarm, same trip. It's pretty obvious at this point that a blown fuse isn't the problem, it's the symptom. Something else is going on. And this is where things get really interesting. The team goes to replace the fuse again, but this time, zap. It blows the instant they put it in. This is the turning point. This isn't some random intermittent glitch anymore. This is what you call a hard, persistent fault. And that means it's time to stop guessing and start a real, systematic investigation. So the team goes into full-on detective mode. First, they check for continuity between the two cable cores. That passes. Okay, so the wire itself isn't broken. Their first thought is, maybe it's a faulty transmitter. It's plausible. But then they run the next test, checking for any current leaking from the wire to the earth ground. And bingo, that's it. One of the cores fails the test, big time. They've found their culprit. And there it was, the hidden fault. Not some complex instrument failure, but a tiny break in the cable's insulation. This little nick was letting one of the cores short out to the ground, which is why it kept blowing the fuse. The fix, once they found it, was actually pretty straightforward. They just ran a new cable from a nearby junction box. And just like that, rock-solid pressure readings and the trip stopped for good. Now, here's the huge lesson from this whole episode. It's a piece of wisdom you only get from being out in the field. A massive amount of the time, I mean seriously, maybe even half the time, the problem isn't the fancy, expensive instrument. It's the simple wire connecting it all together. It's almost always the cable. Remember that. So that first case shows how you can't overlook the simple things. Now let's crank up the stakes a lot. We're going to look at another situation where the root cause was simple, but the consequences were absolutely catastrophic. We're not talking about one pump anymore. We're talking about a failure that brought an entire plant to its knees. Just imagine getting that call. The entire plant has gone dark. It's an engineer's worst nightmare. And the cause? A sudden, total power loss to the I/O cards in the main distributed control system, the DCS. That's the central nervous system of the entire plant. This is a 5-alarm fire, and they need answers immediately. When the team starts digging, they find something really strange. The little green indicator light on the power supply unit is on, making it look like everything's fine. But the second it's put under any kind of load, it just fails to deliver stable power. And the culprit, a tiny little cooling fan inside the unit, had failed. Without that fan, and with the parts getting old, the unit just overheated and gave up, taking the entire plant down with it. This whole disaster pulled back the curtain on a massive design flaw. The brain of the entire plant, this critical DCS, was running on a single power supply. No backup, no redundancy. This is a classic single point of failure. It's basically a ticking time bomb where the failure of one small, cheap component was guaranteed to have catastrophic, plant-wide results. So the fix here wasn't just to replace the broken part, it was to completely re-engineer the system so this could never happen again. They installed a second redundant power supply. They added a smart switch to manage both of them. And they put in a diode module to make sure that if one supply ever fails, the other one takes over seamlessly, instantly. They didn't just fix it, they made it resilient. Okay, so we've looked at two very different stories, a sneaky cable fault and a massive power failure. But you know what? They both point to the exact same lesson, the absolute importance of having a systematic way to troubleshoot. So let's boil down what we learned into a clear, actionable method. Let's call it the troubleshooter's code. If you only take one thing away today, Let it be this process. It's all about resisting that temptation to jump to conclusions. First, identify the actual symptom. What is the system doing, not what you think it's doing? Second, check the entire signal path, from start to finish. Third, as we learned the hard way in case number 1, always verify the health of your cables. And finally, as case number 2 so painfully demonstrated, you have to confirm you have stable, reliable power. So these are some cool stories, but what does it all mean for you in your career? Well, it's about making a fundamental shift in your mindset. It's about going from just knowing things to being able to solve things. And that brings us right back to where we started. Your books and classes are essential. They give you that vital theory. But it's this stuff, getting your hands dirty, chasing down a bizarre fault at 3 a.m., and figuring out why something really broke, that's what transforms you into a real, effective engineer. So, we've seen how theory, combined with a systematic code, can help you unravel even the craziest problems. You have the tools. The real question is, what will you do with them? How will you use this knowledge not just to fix the next problem you face, but to build more robust, more resilient systems that prevent those problems from ever happening in the first place?